Was this yours?
Yeah. Welcome everybody to the Astro Cafe for November the 28th, 2024. Before we start, is there anybody that wants to add anything tonight? Anybody that I should put on the agenda? I know that Randy has a presentation that he wants to give us. David,
Just an announcement for the SIG for next week.
Sure, absolutely. Any other items or any other announcements?
I can just make a quick announcement too.
Sure,
Lori?
Lori, yeah, thank you.
Jeff, it's Margie. I have a question.
Go ahead, Marjie. Would you like to ask it now?
Oh, no, but I, whatever, whenever.
Oh, okay,
Maybe later.
Okay, we'll bring it up after Randy, perhaps.
Thank you.
I can put you there.
Alex, there's another button too.
Yeah, so I was going to just continue with my South America presentation. We left off in Peru. I'm going to pick it up in Ecuador. There's a couple of interesting things in Ecuador. There's some information about the equator, which was interesting, and then some information about the Galapagos, including the volcanism there, and also some sky viewing there. That I found exciting. I'm sure anybody who's had experience in the southern sky is going to find it less than super exciting, but I'm happy to share it because it was my first real experience, south of the equator looking at the sky. So I'm going to get started here. I'll pull this up. Just bear with me for a sec. You guys. Cindy.
Yep, it works.
Well, yeah, but I'm not getting my screen up, guys. So let's see here. Maybe if I take this down.
We've got your email window, so if is it somewhere below there?
Yes, you see that now?
Yeah.
Yeah.
Okay, let's get this onto slideshow then. Share recording. Go through this. Okay, good.
Perfect.
So just bear with me a little bit because I've got to get through the South America portion. Good. Okay, so after Peru, we came to Ecuador. Ecuador is interesting because the equator runs right through Ecuador. And in fact, Ecuador is the country that has a major capital city closest to the equator in the world. That's Quito. This was recognized pre-Columbian time. Quito actually is put together from the original Indian words, middle of the world.
Well,
And you'll see that's kind of interest as we go along with some of the information about the equator. Ecuador itself is set up much like the South American countries on the west side of the continent. There's lowlands towards the ocean, and then highlands with the Andes Mountains, and then interior lowlands. In the case of Ecuador, it's really the Napo River Valley. Napo River is a tributary of the Amazon. So it's sort of the same sort of low, high, low version. These days, Ecuador is really struggling with the drug trade and trying to get rid itself of the drug trade. We were there during the referendum, which was interesting given our recent election. In Ecuador, there's mandatory voting. So every person over 18 has to vote. And the way they enforce it in Ecuador is that you get a certificate when you vote. So if you want to do any transaction at the bank, if you want to do any legal action, taking out a mortgage, or if there's any contract work, you have to show your card. If you don't have a card, you can't do the official operation. So it's quite interesting. They get like a 99% vote. It's quite an interesting turnout. The Ecuador itself, let me just move the screen here. Ecuador itself means equator. It was originally called República de Ecuador, in the original Spanish, Republic of the Equator. So Ecuador has always identified itself with the equator, and that's from pre-Columbian times, when they could see where they were by looking at shadow. And there were times when the sun was directly overhead, no shadow cast, and it was equal north and south, the shadows cast. So the story with the equator really starts back with René Descartes. You probably know René from he's a philosopher from France, cogito ergo sum, I think therefore I am. He was actually a mathematician also and developed the Cartesian coordinate system, which mapped geometrical shapes by mathematical equations. We all use that through school anyway, and probably continue to. His Cartesian modeling was a dual system, geometry and mathematics, and that fit with his philosophical bend, where he was the fellow who really originated dualism as a philosophy. That was a mind-body duality. But from all of that, he also had some interesting views on the formation of planets and the rotation of planets. And it had to do with his vortex theory, which had planets being formed and then pushed through the heavens by some external force. And because of his idea, and because of some of the thought at the time, and also based on some measurements of the Earth, he felt that the Earth shape was prolate, which was bulging at the poles. So that was in the late 16th century and early 17th century. Then Isaac Newton came along, and you know him as a mathematician and physicist. With his ideas about planetary motion and planetary formation, he proposed that the Earth was oblate. That is, it bulged at the equator. Any spinning disk, he postulated, in space would naturally bulge at the equator. So this became quite a controversy at the time. France and England were not exactly friendly. Descartes had started one of the early philosophical movements, and France really held to that. And when this upstart English fellow came along, talking about the shape of the Earth being different than Descartes predicted, it did cause some controversy in France. It also was important because it impacted on the ideas of sailing ship navigation. So it wasn't just an idle issue. So I mean, you probably know this, but the difference between prolate and oblate is just in a sphere. Is it a perfect sphere, or does it bulge at the north-south axis, or does it bulge around the equator? So the prolate sphere is more like a rugby ball, and an oblate bulges at the equator. It's not obviously much of a controversy now, but it's what. Next slide. This started the French expedition, very famous expedition, initiated by the French Academy of Sciences. And they really needed to determine whether Earth was greater around the equator, whether it was oblate, or whether it was great, whether the circumference was greater around the poles or prolate. So this was basically Newton versus Descartes, and really the understory is the French set off to prove that Newton was wrong and that Descartes was right. So what they did was send missions to both Lapland, which was the closest place they could access to the North Pole, and to Ecuador, which was the place they could identify and do some measurements on at the equator. What they were trying to do is do an arc measurement, that is measure the length of 1 degree of latitude, of longitude, so that they could then, I've got that wrong, sorry, it says degree of latitude near the equator, so that they could determine from that the radius of the Earth at as close to the North Pole as possible and at the equator. Measurements they set out in 1736, completed the measurements by 1739. And it was clear, even from their measurements, they were very, very careful about them, that Earth was oblate, that it was slightly larger, the circumference was slightly larger at the equator as compared to through the poles. And I mean, we know that now.
Why would they go to, Jeff,
Yes.
why would they go to Ecuador? Africa's so much closer.
I think it was because it was accessible from the sea, and it was a well-established colony, and they could base themselves out of Quito, which was a large city very close to the equator. So they set out from Quito to do the mapping. So we now know from the World Geodetic surveys done in 84 and 72 that, and of course, that measurement was correct. The circumference or the radius varies by about, I guess this would be half. So the circumference varies by 42 kilometers. So the Earth is, the circumference is larger at the equator by 42 kilometers compared to through the poles. This was shown both in 72 and 84. The measurements there differed by a meter each. So that's where the story starts. So in 36, the French-American Committee of Ecuador raised a monument. And the monument was built at the site of the equator. It was meant to celebrate the arrival of the first geodesic mission in Quito. That was the one that started measuring the Earth at the equator. They put up a 10-meter monument. They called it the Ciudad Mitad del Mundo, the city in the middle of the world. That was supplanted in 79 by a 30-meter tall monument, quite beautiful. And you can visit that currently. This is what it looks like. Lays out the grid, north, south, east, west. Tourists can take all kinds of standard pictures there. This is my group. It's quite a well-established monument, and you can take pictures at their display of the 0 degrees latitude, and the measurements is wrong. So they subsequently found with GPS surveys that that was off by about 240 meters.
Oh,
So that was actually to the delight of the folks that were 240 meters north of the monument, because they could then turn their property into another display of the zero line of latitude, and then have people demonstrating how water twirls one way on one side of the line and on the other side. But that was the story, except that if you're on the monument and you're looking east and you look into the mountains here that are usually covered in cloud, you kind of get a view here. What they found was what they call now zero Katakia, or the 0 point on Katakia Mountain. And they found an equator marker there dating from 800 AD.
Already done.
And it was more accurate than the French mission. It was right on the line. It's a relatively unknown site. We weren't able to get up to it because of certain restrictions on travel at the point, and it was also clouded in. But I've got some pictures of it, which is quite interesting. So this is the original monument, and this is the 12-meter marker that they put also in line with it. And it just sort of sits up on the top of Katakia. So that was the information about Ecuador. I'll just pause for a moment and see if there's any other comments.
Well, actually, being a surveyor, I would have to contribute that actually the Earth is a oblate spheroid, as it turns out. It's pear-shaped. And that monument is not at the widest point of the Earth. It's actually south of there by a fair bit.
Oh, can you explain that?
Well, pear shape is pretty simple. The Earth is pointy at the top, at the north, it's flattened past the equator, bulges, sort of in the South America area, you might say. And then it's quite flat on the southern side.
Is that
We're only talking about
the-
it, but the shape has been well proven with geodesy since, because of satellite positioning systems are very accurate now.
Is that because the weight of Antarctica?
I don't know what the reason is. I only studied the science as it related to surveying. I don't know the geological aspects of it at all.
It has to do with the circulations, the convection in the mantle.
There you go.
Oh, okay.
But I also see that there is a 9-meter wobble with a period of 433 days. So wherever you put that line,
It's gonna move.
it's going to move by that 9 meters. But
Keep moving it then.
Yeah.
No wheels.
it's not the 200 meters. That was bad surveying.
Interesting. So can you is there actually a distance south of the equator that is actually the widest point?
Just search for oblate spheroid and Earth, and it'll come up.
But the definition of equator,
Oblate is just wider at the equator right. So your axis is a minor axis that you rotate.
That term was just manufactured to.
but Jeff.
Yeah.
The equator is not where the Earth is widest. The equator is going to be 90 degrees from the pole.
Right.
Yeah,
And
That's-
that is
that is
astronomical. You can
absolutely.
you can define that, and your point about it being noon, the sun will always be overhead at noon, at local noon. That would be the astronomical definition. Although measuring deviations from that by 200 meters would probably be tricky.
Interesting.
Jeff, did you see what Marjie asked? Oh, okay, you were carrying on. She asked if you could stop the display,
Sure.
get the gallery back, but if you're still presenting.
Oh,
then-
I can go. Oh, I can go back. I mean, we'll struggle to go back, but I'm happy to put it back. Marge, did you want to show something else, Margie?
No, I didn't realize you were continuing. So otherwise, we're just looking at a blank white screen.
That's correct. It's a blank white screen right now. That was my marker to transition.
Thank you.
So is that true of all rotating bodies then, that the equator, I mean, I think the equator would be, I mean, it is of course 90 degrees from the pole, but that would be the point at which the maximum rotation occurs. So wouldn't you expect that to be wider just on the basis of centrifugal force?
Oh, it's not a uniform sphere, right?
Right, well, it's not a uniform.
Where the mass concentrations are.
Yeah. It's like a bowl of lumpy pudding. It can be.
Oh, okay. Just because of the geography of the surface.
Yeah.
Okay, okay, I see. Okay, so using the equator as our segue, about 1,000 kilometers off the coast of Ecuador are the Galapagos Islands. Galapagos Islands is a series of islands that are geologically active. They probably were formed, 2 to 5,000 or 2 to 5 million years ago. They tend to be drifting south, actually a little bit southeast, so that the western edge, which lies over the active part of the mantle, is the newest, and as you'll see, there's still some active volcanism there. I'll just go back there for a sec. Galapagos were, known to pirates and whalers for a long time before they started being recognized after Darwin's travels. Darwin is an interesting guy. We know him from his voyage of the Beagle. Darwin actually went aboard the Beagle as a gentleman naturalist. He self-financed himself on the Beagle. He came from a wealthy family. The voyage of the Beagle was a circumnavigation of the world, looking at all kinds of natural phenomena around the world. They actually spent only 5 weeks in the Galapagos, going through the islands and collecting specimens. There was no eureka moment for Darwin at the Galapagos. His ideas about evolution by natural selection evolved over the 10 years or so as he sifted through his notes and specimens that he brought back from the voyage. As I said, it's an active volcanism in the islands. They continue to form. Similar to Hawaii, over a narrower part of the mantle, of the crust that the mantle is able to break through from time to time, and so there's new landmass being formed periodically. This is from Bartholomew Island. It's probably Pinnacle Rock is probably one of the most recognized features in the Galapagos, other than the various animals. It was featured prominently in a relatively well-researched movie put together called Master and Commander on the Far Side of the World. It was actually, they had special permission to film in the Galapagos. So you can't show you pictures of the Galapagos without going through it. Some of the rare species there. The blue-footed boobies are all over the place on the islands. Various activities, large numbers of them. They dive and fish. The sea lions are through the island. Basically, if you have a species, you either put Galapagos or lava in front of it. The lizards are lava lizards. The sea lions are Galapagos sea lions. The marine iguanas are unique to Galapagos, I believe. So these are iguanas that swim. Frigate birds are found in many places through the island. Flightless cormorants are to be found in many places. They do have flamingos, which of course aren't unique to Galapagos. They do have Galapagos penguins, which I believe is the second smallest species of penguin. I think the fairy penguins in Australia are smaller. Of course, the giant tortoises that Galapagos is named for. Galapagos is actually an ancient Spanish word for a turtle. The tortoises, as you probably know were the favorite of seafarers because they could take them on aboard the boat. They were reasonably docile. They lived for a long time and they provided a great deal of meat. So there is active volcanic activity. We were fortunate that the volcano on Fernandino Island had started up about a month before we came there. So we were able to actually get out by Zodiac at night to have a look at it. The type of eruption that occurs there is a low viscosity lava, so it doesn't flare up, but it runs. And this had broken through a vent, and it was running down along the line into the sea. I'll see if we can. Yeah, there we go. We shot this from the. From one of the Zodiacs that we had.
I don't know. That's amazing, Jeff.
Yeah, it was pretty spectacular night. We could certainly feel the heat coming off. We probably got within, kilometer, half a kilometer maybe.
And you could feel it. Oh, yeah.
Oh, yes, the heat coming off it, absolutely.
Wow.
So, yeah, no, it was pretty cool. Okay, so the other thing that was neat, I mean, again, you'll see why it was neat. We were about 14 minutes south of the equator, and we had a really beautiful night sky. So being exposed to it, basically for the first time. And when I took a picture, I used Sky Safari to shoot the picture also, so I know roughly what I was looking for. So the Sky Safari shots on the left and the camera images on the right. So this one, I was as you probably can tell, I was looking for and looking at the Southern Cross. It's pretty evident in the southern sky. Interestingly, the way you can locate it for anybody who hasn't been there is using the two pointer stars that are bright. This is Alpha Centauri and Beta Centauri, and if you follow them along, they point right to the Southern Cross. But it started me thinking, because the Southern Cross isn't actually in the southern sky. We have this point Polaris in the north, that people are able to navigate with. So I was trying to figure out how it was they used the Southern Cross to navigate by in the Southern Hemisphere. And in fact, there is a way you can calculate due south from the pointer stars and the Southern Cross. And if you draw a line between the pointer stars, between Alpha and Beta Centauri, go halfway between them, take a perpendicular, drop it down, and then come down from the Southern Cross 4 distances from the top to the bottom. Where they intersect, if you then drop that line to the horizon, that's due south. So that's this. You take
Nothing there to aim your camera at so that you can track things.
That's right.
It's impossible to align to the pole.
So just to illustrate, take a line, drop a perpendicular, follow it along, go 4 distances from the top to the bottom. There, the X, and then drop that down. Should be due south. So that started me thinking, the other thing that was really neat for me. Actually, given our discussion last week, I thought I'd put this one up. This was obviously Orion. Orion's in the western sky now, on its side, which is a position I'd never seen it. I obviously we're used to seeing it in the southern sky, and with a slightly different angulation. So the other interesting thing to me was, of course, I couldn't see Polaris. And yeah, I know you can, I didn't do a great picture because I didn't show right to the horizon. You're going to have to trust me, and I showed it here. Polaris. Yeah, in my picture you can't see Polaris. Polaris isn't evident at this time of night anyway in the southern sky. So I started wondering, because Polaris doesn't sit exactly in the north, how far south you should theoretically be able to see Polaris. Well, there's of course an answer to that. The declination of Polaris is 89.34 degrees. So Polaris should be visible from 0.66 degrees south, and with refraction, it's possible to see it from more than 1 degree south. Yeah, so it's theoretically, I at some point in the night I should have been able to see it, because we were about, what did I say, 14 minutes south. So the reason Polaris is visible now as our marker is because of the precession of the Earth. The Earth has a wobble that is about a 26,000 year cycle, where it wobbles like a top. It doesn't go back and forth, it goes around. So in about the year 14,000, Polaris will no longer be the North Star. In fact, we'll lose that a long time. And it's actually Vega that will be the North Star in the year 14,000, as the Earth wobbles around and hits the other extreme of its wobble. So the other thing that was really interesting in the Galapagos was just the nature of the lava. Obviously a lot of it's cooled, and it came in different forms, and this is because of the flow that you got with the lava there. There's basically 3 major types of lava flow determined by their mineral composition and their viscosity. The lava, and that's determined by the heat of the magma that comes through. This is a basaltic type of lava, which, as I said, was low viscosity and flows rather than building up and creating sort of shield walls. So a lot of the island has this appearance, where you don't have plants, you don't have any growth. So that is the end of Galapagos. Any thoughts or other comments there?
I will contribute that from Costa Rica, which is about 10 or 12 degrees north latitude, I could just make out Polaris and use it for alignment. So it was scraping the northern horizon. So I have my serious doubts you could do the same at the equator.
Well, you'd need probably perfect conditions, and probably being up a mountain might help.
Or on
right?
an ocean, yeah.
Or on an ocean, yeah. You're not going to see it on, if the skies are like here, you're not going to see anything on the horizons.
Well, with it being very close to the horizon, wouldn't you expect it to rise a little bit with the rotation? So there might be a time of the night that it would become more evident. I mean, because it's no longer, fixed in the sky, but rather rising and falling. And that was one of the things I was trying to figure out,
No, it can still be fixed.
It's fixed. It only wobbles by half a degree
yeah.
around the axis. The axis isn't moving.
Oh, no, but that half a degree, that's the point. With that half a degree, I mean, we're talking in tiny amounts of distance. I mean, it's not that it would always be visible.
No, it would be half the night it'd be gone, or half the 24-hour period it'd be gone, because it'd be below the horizon.
Right.
And seeing something mag 2 at the horizon is probably
Not gonna happen.
not going to happen too often. That makes
Yeah,
sense.
no, for sure. No, you need absolutely.
But you wouldn't polar align, like polar alignment would be really terrible, because you don't want to a line off of something that's only 1 degree,
Yeah.
plus or minus 1 degree.
Yeah.
Jeff, you should turn off your picture so people can see you.
Okay.
Oh, sorry.
Okay, now you can see me. I don't know. Picture of the ocean was probably better.
I
Anyway,
have a question.
yeah, of course.
Yeah, it's not really related to astronomy, but it was about your final slide and comment. So
Okay.
about plants not growing there. I'm curious, what was distinctive to me about that terrain was that there was no soil, right? Which is why there's no plants, I assume.
Well,
So is there soil in areas in the Galapagos? And if not, why is it not forming? Is it because the lava is so frequent?
I'd say yes and yes. I mean, there are areas that there's absolutely growth. And it's because there's been long enough for the lava to break down. I mean, as all volcanic islands, the lava isn't permanent. The lava breaks down, forms bits of soil, and the part I showed you was some of the newly formed, quotation marks, newly formed island on the western side. So I think it all started with cooling lava, and then the lava gradually breaks down and certainly creates soil, and then with soil you get some seed and you get some growth. There's 3 different types of cactus that grow in the Galapagos. So yeah, there's absolutely growth, and I mean, there's a small city there in one of the eastern islands, and there's a permanent population on the islands. It's sort of like Iceland, you can't immigrate to it. It's got a reasonably controlled population. They're very obsessed about recycling. It's just really cool. How little garbage there is and how much things are recycled. Were you there recently or a while ago?
Myself?
Yeah, was
No,
that your question? Or are you just wondering?
No, yeah, I'm just curious.
Yeah. Oh
And
yeah.
because it's so identified with creatures that can leave, with Darwin and his birds and the turtles, right? I wondered, is there much?
Well, we were there in 2019. We spent 4 days on 2 different boats. And we traveled to a number of different islands. And there's quite a difference between the islands. They get much more barren and more exposed to the weather to the north and west. But as you go down further to south towards the east, they get quite eroded, and the ecology changes quite a bit from island to island. And that's what really struck Darwin, because the fauna and flora is completely different from island to island to island, other than sea lions and some of the birds that are migratory. But the land animals are quite different from island to island to island. And that's because the ecology was quite different from island to island. If you get a chance to go, you should. It's a fabulous experience.
Yeah, that's well said. Thank you.
My daughter was there this last summer. She had a great time.
Yeah, you have to be accompanied to go there. You can't just wander yourself, and they certainly there are some spots you can't go to. There's some spots that are out of bounds, and they've got very good information about the places you can go. And you're quite right. The flora and fauna do differ. It does tend to be, the older islands that tend to be, of course, more eroded with more growth. Older in quotation marks. Marjie, if you're okay holding the question, because Randy had a presentation that he wanted to give us about stellar classification. Are you set there, Randy?
I will be set as soon as I share my screen.
Before we go, great presentations, Jeff. Thanks, sir.
Jeff, it was fantastic.
Oh, thank you.
Okay, I got some laughs and some people will know why it's particularly funny later on. Anyway, so yes, last week I asked the question, what would it be like if Earth orbited Rigel? And then at one point in there, because it was a free-form discussion, but we started talking about how Rigel in Orion is a B class star, meaning it's extremely hot. It's about twice as hot as the sun. And that makes for all sorts of things, like the Earth would be inundated with ultraviolet light instead of visible light. Anyway, then Annie Jump Cannon's name came up, and I thought, this is such a great story. I have to do some more research on it. And when I research something, then I share it with all of you, my dear astro friends. So I'm not going to go through this slide in any detail. Every line here is worth an Astro Cafe talk, but let's just do it quickly. That throughout the 19th century, people were like collecting huge amounts of new data about the stars, and there was no concept of where this was going to go. I mean, they went from saying, oh, look at the pretty points in the sky, to what we now call astrophysics, understanding what the stars are, how they're made, how long they live, their masses, all this amazing stuff. And it just blows me away having this complete, like it's as wild as taking a ship across and finding the Galapagos. Anyway, so first thing is when you put a prism up against the sun, you see a rainbow. But when you look really closely, you see that there are some dark bands. There's some parts of the spectrum where the light doesn't come as strong. And then next decade, Fraunhofer did very detailed work and measured these wavelengths. And we call them Fraunhofer lines now. And there's actually thousands of these lines, but there's some very prominent ones. Then Kirchhoff and Bunsen, who's famous for the Bunsen burner, they were in the game of looking at the spectra of chemical elements which you heat up, and they provide light, but they don't do a continuous light. They have very, very specific frequencies or wavelengths. And now, with an extra couple of hundred years of analysis, we actually study this quite well in terms of quantum mechanics and atomic theory. And there's some excellent science that they didn't have close to knowing what it was about, but they did know that when you heat up sodium, you get two really bright yellow lines. And when you heat up hydrogen, you get this series of frequencies. I mean, I should talk about wavelengths, which are they follow beautiful, simple mathematics. Anyway, and they were the two that said, holy, here on Earth, we're seeing the same things on the sun. And it was the first recognition that it's the same. There's no difference between the elements on the sun and the elements on Earth. That's a big one. But then during the eclipse of 1868, there were actually about 4 independent measurements of the of the spectrum of the corona during the eclipse. But this fellow, Georges Rayet, he said, he was very bold and said, I don't recognize this line. It must be an element that we don't have on Earth, and we'll name it after Helios, after the sun. So that was the discovery of helium. It was not found on Earth. Now, there were a few people who started taking photographs of spectra of stars, but important for this story is a rich fellow in upstate New York who built an observatory and took an astro spectrum of Vega, and then he died. But he left a lot of money, or I think it was actually his wife's money that he was spending. Anyway, the important thing is I missed a page. Didn't I?
No. 1881.
Okay. Oh, I know, it'll be the next page. So, new chapter. The Harvard College Observatory. Mostly its job was to figure out time because they needed to tell navigators in Boston when is noon so that they could set their clocks, their chronometers, so they can measure longitude as they go around. But for some reason, they passed by some very good astronomers and invited or hired a physicist, heavens, to be the astronomer for the Harvard College Observatory. This was a whole new thing, and Edward Pickering was quite a visionary, and with the development of astrophotography, he figured that the pathway to understanding the sky was by doing these big surveys and studying every single star. And that took a lot of work. And for a number of reasons, some honorable and some not, he found that it was a really good idea to hire women to process the plates, the photographic plates that were taken with their telescopes. And in particular, one of the first women that he hired to do this kind of boring, very painstakingly detailed work was his maid, Wilhelmina Fleming. And she turned out to be awesome, and was quite quickly put in charge of this whole endeavor. And yeah, so, oh heavens, I have missed the slide. Anyway, the important thing, going back to this, is Henry Draper's widow was, oh, you know what?
You didn't miss the slide, it's just the bottom.
It's at the very, it's missing on the screen there.
It's not missing on the broadcast.
Oh, good. The important thing is 1882, Mary Anna Draper put a lot of money to support. Oh, thank you.
Let's see if we can get rid of it.
To support the Harvard College Observatory. And with this money, Pickering hired Wilhelmina Fleming, and what she, oh my goodness, I'm doing a terrible job today, because the other thing, another chapter, is that Harvard College Observatory was not the first place that people tried to systematize their observations of stellar spectra. And in particular, Angelo Secchi and that is Society of Jesus. He was a Jesuit, but he thought that being an astronomer was way more interesting than being a priest. And they put him in charge of the papal observatory, and he photographed thousands of stars, and he made 3 broad classes. And so the blue stars were called class 1, and that's where we get things like Rigel. Remember, that's what started this whole rabbit hole, was wondering about how they knew about Rigel being a blue giant. The sun is a yellow star, and you can see it has a lot more of these spectral lines in it. And then the red stars, class 3, like Betelgeuse, also in Orion, has a gazillion lines in it. And so that was kind of the earliest spectral classification. But what they did in Harvard is they would put a prism in front of the telescope. And by doing that, every single star on the plate would have its own little spectrum. And then, so they would take a picture without the prism, and they would use that to get the position and their brightness, but they would also take a picture with the prism, and then they would get those fine women, the calculators, the computers, to classify them. And Fleming made this set of, I don't know, 20 or so classifications named from A to O, and without any physical sense, but they were kind of from the really bright hydrogen lines to the O, which, keep in mind, O was the furthest away from A in Fleming's classification, but O doesn't have any hydrogen, Balmer lines they're called. Okay, now then in 1887, there were 11 women in Fleming's team, and at the time, she was older and she was put in charge, and so she was kind of the head of that group. But then Antonia Marjie showed up on the scene. She came highly recommended from Vassar. Is that the name of the college? I mean, the thing is, women were getting educated, but then they didn't really have any jobs that they could go to. But Marjie came very highly recommended, and also she was Anne Murray's Draper's niece. So she had an in there also, because all the money was coming from her aunt. But despite that, there's no question that Marjie was one of those incredibly talented, capable people. And what are you going to do if you're a talented mathematician, female, in the 1880s in the US? I mean, there's not a lot of jobs. But it did put Pickering in a bit of a pickle, because she was the new person, and it didn't make sense to put somebody who was upper class and much more experienced and capable than anybody else, putting her under Fleming. Anyway, so he did what a modern professor would do with a grad student. He gave her a specific job. Said, okay, we're photographing with this new telescope that we just got. We're photographing the spectra of the brightest stars in the sky, and go for it. Figure out, do the thing. What's the story? And she went wild. She classified things with the widths of the lines and their spacing, of course, and she had a whole bunch of things that she measured on each spectrum, and she came up with this very difficult classification scheme, but it was awesome. This podcast I listened to said it's like classifying birds. So if you don't know how birds are related to each other, if you're just, you land on Earth and your boss says, we need a classification system for all the birds on Earth. What are you going to measure? Is it the beak? Is it the size? Is it the color? Anyway, so she did everything. And it was a very, very important step, but it wasn't something that people have continued to use today. Let's say that. Oh, another aside. This is a very complicated subject, but I love it. So there's going to be just a lot of asides as we go along. One of the weird things were those O class stars. Remember Fleming's list? If there's lots of hydrogen, it got A, B, C. But if there was no hydrogen, then we got the higher letters. And among them were these O and B class stars, which had these lines. And they got called helium. Remember, that was what happened in 1868. But it was never seen on Earth until the chemist William Ramsay. Oh, and they called these lines Orion lines, because as well as Rigel, there's another blue giant in Orion, if somebody knows their stars of Orion. But so these weird lines were called the Orion lines. And Ramsay took this, it turns out now we know it's uranium oxide, but he took this mineral, put it in acid, heated up the gas, and he said, by golly, I recognize those lines. Those are the lines we see on the sun. And that was the first observation of helium on Earth, which I think is really cool. Anyway, that's 1895. So the 1890s was when all of this stuff was happening. Very exciting time. Then another extremely capable woman came out of Vassar or Radcliffe or one of the female colleges, and she got hired. Interestingly, if you saw, what was the name of the play about Henrietta Leavitt, Glass Universe? What was that? Was that what it's called? Anyway, the play that we saw at the Belfry about Henrietta Leavitt, who was their colleague and figured out the Cepheid variable law. Anyway, she was hard of hearing because she had scarlet fever and it attacked her ears. Anyway, similarly, Annie Cannon also as an adult and a school teacher, but she got scarlet fever, lost a lot of her hearing. And I think that this job was a pretty good place where you could work even if you couldn't hear. And so that might have been another reason she was attracted to this. Anyway, she was tasked with doing these stellar classifications, and damn if she wasn't good at it. And one place I read that she could do 200 stars per hour. And the way that they would do it is there would be one of the computers with a magnifying glass looking at the plate, and then another one would be taking notes. And so she would just be, just imagine going through, and she could see down to, they said that she was good and very accurate all the way down to magnitude 9 in these photographs. So she was doing thousands and thousands of these classifications. And she came up with a much simpler scheme. And the podcast that I watched was, it was really good about not just talking about what these people were doing, but also some of the philosophy behind it. And there's no question that this classification based on Wilhelmina Fleming's classification, but she simplified it down to 7, and she put them in this order: O, B, A, F, G, K, M. Okay, so you see that's not in the alphabetical order that Wilhelmina had envisioned things at first. But and it doesn't fit all the stars. It doesn't do like Marjie did. This was for explaining most of the stars, and she actually did subclassify these because you could say a number after the letter. So the sun is G2, for example. So G2 means it's more G-like than K-like, but a G9 is almost a K. Okay, so it goes from G0 to G9, then it goes K0. So it's like a decimal system. Anyway, so then some smartass in Princeton, where they did not hire women to be astronomers, heavens, he made up the mnemonic that I certainly was taught 40 years ago as an undergrad, and I think many of you will know it. Oh, be a fine gal, kiss me. And apparently the computers at Harvard accepted that as their acronym to remember the order, but it was initially meant, according to this one fellow, to be kind of a snide remark at the people who are considering that they can actually be competent astronomers. But the fact is they were excellent, and everybody recognizes that. Anyway, my favorite mnemonic is only bad astronomers forget generally known mnemonics. It is beautifully self-referential and way better than the better known mnemonic. So I highly recommend that you remember this one, and then you can do your stellar classifications on your own. Or more important, when you read something like saying, Plaskett had as his program here at the observatory in Victoria to measure the spectra of all the O and B stars, then you'll say, oh, that means the hot ones. So that was their goal, was to measure all of the O and B stars. And then with that, by looking at the spectra, they figured out the structure of the Milky Way. Awesome. Okay, so I did not take any, I just did an introductory astronomy course. I did not go through the whole set. So my astronomy is at a very low level compared to what any undergrad would do. But apparently this diagram is the sort of thing that every astronomy student gets to know to the point of being nauseous about them. But you will, in labs, have to classify tens of spectra on the basis of what lines you see. So you can see that the hydrogen, I can use my pointer, the hydrogen lines are really visible in the A and F classes, but as it gets cold, then you don't actually ionize the hydrogen very much, so you don't see those lines very much. But as you get too hot, then the hydrogen gets so ionized that there's no electrons around it, and so it doesn't absorb any light. And so that's why it goes from no hydrogen lines when you're in the O class to lots when you're in the middle. And then as it gets very cool, then they disappear. So by looking at the different strengths of different places in the spectrum, you can actually measure the temperature of the star, work out what class they are. And I just want to say that this YouTube, it's totally a COVID era YouTube. This is an astronomy professor. He obviously is, this is just an undergrad lecture, but there you have his bedroom, you have his keyboard in his background. But it's really good. And, you know, he goes to this website where they have 1 million spectra, like it's a real research website, and he just clicks on them at random, and then he says, okay, let's classify this. And then, you know, he'll say, okay, so the temperature is medium, there's weak to moderate hydrogen features, strong ionized metals. So, you know, you go through it, and then he figures out, okay, so this particular star is going to be like an F5. And then they look to see what actually the official classification is. And he's usually within, you know, a couple of tenths of what it's considered. And he just did it by doing this diagram. So if you're into this sort of thing, I highly recommend it. And I'll get Joe the website to put into the YouTube. And the other, I'm just closing with this. My other references, I haven't read Glass Universe for, I think, 4 or 5 years, but it has remained in my head. It's one of the really, really great astronomy books, and I highly recommend it. It's about the computers at Harvard and beautifully researched. It is not done at a technical level. It explains things, I think, extremely well. And if you don't want to read the book, there are on YouTube, probably 3 hour-long lectures that she's given in different places about it. And she speaks beautifully about it. And she loves these women, and she really gets into their heads, I think, and I highly recommend. Now, far more detailed is this podcast that I found. It's kind of slow, and it kind of says what they were doing week by week in 1893. But it's so cool if you give it the time. So that a lot of what I've been telling you about came from this podcast. And I hate that it's only had, in 4 years, 131 views. It was 130 before I watched it. This guy did a lot of work, so I think you should watch it. And I think with that, I'm finished.
Thank you very much, Randy. Anybody have questions, Randy? Any follow-up on the stellar classification or any further comments there?
No, I just say that Davis Sobel this week has published a new book on Madame Curie and a whole group of females that were associated with her. So it really focuses on the struggles that were illustrated in the Glass Universe.
What's the book called? Do you know?
Yeah.
Oh,
I
okay.
read the book review on it, and
I do want that.
Click on Amazon, it'll be there.
Hi, I have a question for somebody. I noticed that the absorption lines and the emission lines lined up. I understand emission lines, but I don't understand absorption lines and why they line up with the emission lines. Can anybody tell me that?
Sure. So if you think of the electrons jumping orbitals,
Yep, got that.
it can jump up or it can jump down. And there's a difference in energy between each of those orbitals.
Okay.
So if the photon is the right energy, the electron will say, oh, I like that one, and jump up an energy level.
And that gives off, that absorbs a
So,
photon?
so that absorbs the same wavelength or the same frequency as it will give off when it jumps down an orbital.
Oh, okay, great, good. Exactly what I needed to know. Thank you.
That was well explained, Dave.
Thanks.
Good. Marjie, did you want to raise your question at this point? Or Lori, was there some further comment?
Well, I think a couple of, I think a couple of other people had their hands up just right
Oh.
after Randy
I
finished.
Missed that then.
Who was, David, you had your hand up, and Sinead, you had your hand up as well?
They were clapping.
Mine was an applause.
Oh, sorry.
I
Okay.
would too, but I do have a question though.
Just go ahead.
So it's speaking from my naivety, so I just want to step back from what was just presented and say, okay, so am I right in interpreting that what's going on here is that the light is emanated from a star and it's analyzed in a spectrum, and the spectrum then is analyzed in terms of giving information on its temperature and composition?
Absolutely.
Bingo.
Just to check.
Okay, and to be specific, the light that you see on a star comes from what's called the photosphere. So there's this transition from where the body is opaque to transparent. And so what you're seeing is the light coming off this glowing sphere of hot plasma, and the lines are the gas in that transparent part just above that are absorbing some of the light. Okay, so what we're looking at is what's happening right at that transition from the opaque body of the star to that transparent stuff above.
Okay then.
And Gary, the reason that you see helium emission lines during the eclipse is you're looking at the photons coming off the hot helium in the corona, whereas normally when you're looking at the sun, that stuff is so faint that you don't see it. What you're mostly seeing is the helium in the corona absorbing the light from the photon, from the photosphere below.
Okay, that's an important part too. I get it. Yeah, good, good, very good.
Super. Was there anything else?
If I could put a pitch in from my image on Zenfolio, I put in the descriptor of what you're looking at with narrowband filters. So we're actually looking at the spectral lines with our camera so we can actually see the gases.
Will you be able to show that when we come to the photos?
Sure, sure.
Be very, very useful, especially following up on the discussion today. Just Margie has one thing, and then we're going to get to pictures.
Sure.
Okay. Margie, go ahead.
Okay, thank you. Based on Natasha's information from last week, I have been doing some online reading about the solar wind. So I understand that the solar wind is made up of particles of protons and electrons. And then, which means ionized hydrogen and helium and heavy ions, such as nitrogen, carbon, neon, argon, silicon. What I cannot find in terms of research, it always talks about particles of protons and electrons, but I can't actually find information that says, are those particles actually particles? Are they bits of things? What are they?
Dave, go for it.
Yes, they are particles. They're not, they're the parts of the atom that have been stripped away in the corona and fired off of the sun that are coming by.
Okay, so if you could, if it were possible to see those particles, what would they be? What would they look like? What would they be? Are they something?
Some of them will, some of them will be electrons,
Yes.
right?
Yeah, but
Some
you can't see an electron, can you?
well, it can emit a photon.
So
If
it's
it's just
emitting light.
traveling, if it's just traveling along through space, it's got to bump into something or come
Right.
close to bumping into something.
Right.
So if it's going really fast and it comes across a proton, which is really a helium nucleus.
Yeah.
Hydrogen.
Hydrogen nucleus, sorry. The first thing it does is it puts on the brakes. So it has to brake hard, and it's actually called braking radiation, because it goes, hey, there's a photon. I want to have a relationship with this photon. So it puts on the brakes hard, and it emits electrons. It's going really fast and emits an X-ray photon. And that's exactly how your dentist makes X-rays in the dental chair to photograph your teeth. And then it sort of stops and joins with the proton again to form a hydrogen atom. That sort of jumps down the energy levels, and that gives the hydrogen spectrum as it jumps. Sometimes it jumps down multiple levels at once, sometimes it jumps down one level, and different kinds of orbitals in the same orbit, and that's what gives us the hydrogen spectrum, all the hydrogen lines. And some of the other particles are what we call alpha particles, which are really helium
Nuclei.
Thank you. And protons themselves possibly streaming out, and that's collectively the solar wind that we call, along with the photons given off by the sun.
Marjie, there is no
Yes.
microscope that can see them.
Right.
But there are very important physical observations you can make. One thing is you can put a big sail up and actually move a spaceship using the solar wind pushing on the sail. They've actually started doing that. It's the cheapest way to make a spaceship travel away from the sun, is you put up this huge sail, and it actually, the momentum of these particles banging against it will push the spaceship.
Yeah, Planetary Society did that.
I'm sorry, who did? Planetary Society. So they are real particles. They're just tiny.
Marjie, do you know when we got our first samples of the solar wind back on Earth? Neil and Buzz brought them back in Apollo 11.
Oh.
And if you don't believe me, there's two ways they got it. If you look at the pictures of that moonwalk, you'll see, you see Neil and Buzz, or well, usually it's Buzz standing around, and you see the flag, but you also see something that looks like a strip of aluminum foil hanging there. And that was specifically brought along to collect solar wind.
Cool.
And the experimenter was a guy named Johannes Geiss, who was from Switzerland. So the nickname for that experiment is the Swiss flag. And they flew that on several of the moon landings and just left it out while the astronauts were walking around the moon, and then folded it up, brought it back with the samples. And on top of that, of course, there's these rocks that have been sitting in the sun for millions of years that also have some of this in there. So they were able to, detect them in the lunar samples.
Wow.
So that's one of the more interesting. But if I was sitting at my computer, I'd pull up one of those pictures right now and show you. But if you look at some of the pictures of the moonwalk, you will see the Swiss flag there.
So Chris, when you say it collects solar particles, it's collecting electrons and protons.
Yes, yeah.
So you're actually not being able to see the particles. You're seeing the effects of the particles on the aluminum. Is that what you're seeing?
I think, yeah, I think so. I'm not, you know, I'm kind of stronger in what the astronauts did than what the scientists saw.
I'm
So,
not strong in either one of them. Okay. So Margie, those are teeny weeny particles. They're the fundamental building blocks of all atoms, and you're not going to see them whizzing by, just like Dave said. You can see what they do when they hit something else. That's what you're looking at.
So they're little tiny little things of energy.
That's the word.
Yeah, the
Well,
energy.
that's-
Yeah, that's right. Yeah. And they're particles. They're particles and waves. Photons are particles and waves. But anyhow, we don't want to get into physics here, like we could just like
Okay.
Well,
I did have-
with physics.
I did have a question that's physics-like. Just building on your question, Margie, is it answered for you?
Yeah, yes.
It builds
Yes.
on what you said though, because I'm curious. So this is a question I've had, and I know it's impossible to answer. So, but maybe just yes or no, if anyone knows. I happen to have been with a group of some of the leading physicists in the world with the Dalai Lama. You know, I mentioned I lived with the Tibetans for a week, and Anton Zeilinger, I don't know if you know who he is, was there. From the University of Vienna. And within a few months of that meeting, he did the first successful experiment proving entanglement using a particle accelerator. And so I know about particle physics, and then there's astronomy, and even though there were astronomers there, I always wonder, how do they relate, if at all? And it sounds to me like, I guess, does the solar wind create the same effect as a particle accelerator? And can these effects be observed at any point, or does it have to be in a controlled environment like an accelerator? Does anyone know?
It sounds to me
Well-
like we need to invite Dr. John McDonald to give a talk about particles, because he's a particle physicist and he's worked on years and all that sort of stuff.
That would be great.
It would take a whole evening. We have to persuade him to come back and talk to us.
But you're right, Sonia. Both things accelerate particles, the sun and the particle accelerator.
so I was just gonna say, for Margie's benefit, I mean, everything you're looking at now is made up of those protons and electrons and also neutrons combined together into elements, combined together into molecules, including every person you're looking at here.
Okay. Yeah.
That's the building blocks of everything.
Yeah.
Yeah. Yeah.
Okay. Yeah. Whereas I'm like physically, it's for a non-physicist, it's easy to think of particles as, for example, dust particles, like something that is very tangible and seeable.
Yeah.
So, but obviously the word particle is a terminology that works for lots of things, but it's
Yeah,
not
it's a model. It's a model. It's a useful metaphor.
Yeah.
You're absolutely right.
Well, if you want to think of it this way, the dust we can see is a big clump of them. Or potentially billions of them, right?
And to the 23s.
Yeah.
And is it not that the basic particle is a photon? At least that's what they're measuring in particle accelerators. So they can see it technically, Margie. It does leave an imprint on something.
They can't see it, they see its
No.
effect.
It's
They
a
can,
fact.
they can detect it.
That's where it gets really weird, because you can treat it either as a discrete particle or as a wave.
Mm.
It's weird.
Very, very good questions, Margie and Sonia. Very good questions.
Thanks very much.
Really strange territory.
So we're rolling over to the photography section. I know that there's been some activity with the comet. Dave, also, hopefully you've got yours scrolled up enough to show us the stellar information. Is there anybody who I can queue up to show some of their photos?
Yeah, I can show you the last few comet shots that I've done.
Perfect, Dave. I know you've been working hard at those. I've seen a bunch of them. That's great. Well, maybe why don't you go ahead first, Dave, and then we'll go over to Dave Lee. Why don't you go first, and then Dave Payne will have a look at yours. If
Yeah,
that'd be
no
okay.
problem. So this is the last one I did. I've done a number of them. They kind of all look very similar. One thing I should note or let people know is that I tried really hard to use as little technology as possible to take these pictures. So for the first few prior to this shot, they were all taken on a tripod with just multiple, I would say, relatively short exposures. They were like 1 or 2 second shots, but a whole bunch of them, like hundreds. And I was able to get a lot of detail, but I eventually succumbed to using a tracker. And Reg said, "Well, it should be a good night after 8 o'clock." So we kind of patiently waited while we were working in the shed. Unfortunately, I came out to see that my lens was covered in fog or in dew. And I thought, oh boy, like I don't have anything. So I went home and I was pleasantly surprised that I only lost, out of 150, I only lost about 7 exposures. So that was pretty good. This one, I should also tell you, this is one where the stars are sharp and the head is somewhat kind of smeared. I'm still kind of working on a head aligned shot, but I've not been very happy. There's a lot of artifacts that are associated with that shot, so I don't have that here. So I thought what I did was I would shoot with a longer lens, and that's basically what I did. But there were a couple of things which I found really interesting outside of the detail in the circle that I show. There was a star called Sigma Ophiuchi, and because there's so many stacked and so much haze in the sky, aside from dewing, it's kind of lost a little bit of its color. But to go back and reference Randy's classification, this Sigma Ophiuchi is a K-class star. So it should be kind of orangey red, but because of the haze, it got quite diluted. But you can see it there. One of the interesting side effects of haze is that it actually makes stars bigger. So that actually helped kind of emphasize Sigma Ophiuchi. So yeah, I'm hoping to get some more shots, maybe if the weather cooperates. But the comet is basically swinging out of Ophiuchus now, so it's heading out and fading. So I don't know if anybody's seen it since this date, since the 24th. But yeah, I'm still hoping to see it maybe one more time. So any questions or?
I just like to say I was there and I know about the conditions and the atmosphere neglected to read Environment Canada's forecast.
How dare they?
Unprecedented. Disappointed and I felt betrayed. But anyway, Randy did David did a remarkable job capturing these images. I'm surprised that anything came out at all. So
I am too.
Well, that's really excellent, David. Dave Payne, would you show your shot?
Sure. I just got to share here. So So it's by no way means an award-winning image or anything like that, but it is a unique object, and we don't really know what it is.
Pretty spooky. I mean, this is the right week to see, I think.
Well, lately I've begun the practice of explaining what the thing is that you're looking at. And I didn't know what this was, and no one seems to know what it is. So I rather adeptly changed the topic in my explanation. So what I'll leave you read this. If you go to the Zenfolio site, or if you go to the Astrovin site, whichever one you'd like to go to, I talk a little bit about narrowband. Now, some of the images us photographers take are broadband colors, and we just use red, green, and blue filters, just like a camera you're taking snapshots with. But we also do these narrowband, and what narrowband images are after is trying to just let in those spectral lines like you saw coming out of the sun. So instead of looking at solids and liquids, which generally give off broadband colors, we're actually trying to see the spectral lines given off by specific elements in their fingerprint of narrowband. So there was nothing much scientific about picking what elements and what spectral lines are used. It was more like, okay, it's got to be in the visible part of the spectrum. It doesn't really have to be, and modern telescopes take narrowband images of non-visible range. JWST takes a lot of infrared images. So, but at the time, let's make sure it's in the visible range. And so the second criteria is we want relatively strong spectral lines so we can take pictures easily. And the third thing is we don't want each of those spectral lines to paint the same picture. We want those spectrum to come from different areas. So the red in this picture is the hydrogen alpha. It's the first in the visible spectral lines given off by hydrogen. And the second sort of color you see in here is this blue object that we don't know what it is. And that's given off by one of the spectral lines of an oxygen atom. And the third one, which in this case overlaps with the hydrogen very well, is a spectral line given off by a sulfur atom. So the whole region here is being bombarded by UV light, which is light we can't see, by all the stars in this image. It's kind of hard to get a sense from the red stuff or the blue stuff how far the stars are. Some are way in the background, some are in the foreground. But the ones that are proximal are the ones that are giving off this UV light. And it's like a sledgehammer. It's going around knocking the electrons right out of the atoms. It's breaking any chemical bonds they have and knocking off knocking off one or more electrons. And then the nucleus start going around collecting those electrons. And as I was saying in that X-ray example, but once they find the electrons, they capture it, and then slowly get that electron jumps down energy levels. And those produce those spectrum, and that's what we're seeing in these images. Now, some people like them because they show a lot of detail when you're going after specific gases. Some people don't because there's somewhat unnatural and made up colors that we have to assign them to. But there's one anecdote that I want to talk about because it goes to what was spoken about before in the discovery of helium. Was they saw a spectrum and they didn't know what it belonged to, and later they discovered helium and found out that helium was giving off that spectrum. So then the problem was solved. In this case, this blue light we now know is given off by oxygen. But we couldn't make oxygen in the lab give off this light. So no one knew what this gas was that was giving off this light. So they made up a new name for a new element, and they called it nebulium because we tend to see it in nebulae. And so we didn't know where this nebulium was coming from. We just knew it gave off this color of light and everything was great.
When?
This would have been around the turn of the 20th century, I believe, is when it got its nebulium. It was later, I think it was in the 50s, when it was later found that in jumping energy levels, that's not the only way a gas can, an electron can move down. It doesn't have to give off a photon. It can do another thing. It can bump into a neighboring molecule. Now, when it does that, it sort of heats up the other molecule, gives it a nice warming, and that's how it gets rid of the energy rather than giving off a photon. So when you look at oxygen down here and you play with it in the lab, this has a half-life. It takes about 3 minutes on average for oxygen to release this blue photon. Well, in that 3 minutes, a whole bunch of other atoms and molecules are going to bump into that oxygen. In this case, it's an ion. It's going to bump into that oxygen ion, and it's going to take that energy away in the form of heat. So the oxygen we had here on Earth never had a chance to emit that color photon. And they didn't know why at first, so they just said, well, as it turns out in space, it's much less dense. So there's a greater chance that the oxygen ion is going to float around and not get bumped into by any other molecules. In that 2 minutes, it's waiting to emit its photon. And then finally, it emits it after 2 minutes wait because, hey, there's no one to bump into. So they called this emission spectrum forbidden. And forbidden, I think, is an indication of bad parenting because I always thought it was a binary thing, but forbidden in terms of that means, well, it doesn't emit down here on Earth, but like once it's out and about in outer space, it's free to emit this blue color. Does that all make sense?
David, are the colors that are assigned here, the hydrogen and the oxygen, completely arbitrary?
So the three primary colors that you see, the three primary spectral lines that we go after, one is hydrogen and one is sulfur. Those are both red. Okay. So in this image, I more or less made them both red. I made the hydrogen a little orangey red and the sulfur I made redder red. And then the oxygen, this blue greeny color is pretty close to the actual color it gives off. But this is really a 2-color image, except for the stars. It's really a 2-color image. When you get to 3 colors, you're left with a quandary because 2 are red and 1's greeny blue, and you have to assign one to red, green, and blue. So then it becomes whatever you choose. Now, Hubble had the same problem with their images, and they decided to give sulfur red, hydrogen green, and oxygen blue. And then they did a little funky thing and took the green away because no one really liked green. And that became known as the Hubble palette. And that's mostly the standard. But if you look at a JWST image, right, they'll have an infrared. And that's not really red, but to show it to you, they have to assign it to a color you can actually see. So it's just basically using false color, and you can call it artistic freedom, or you can go with convention or whatever you like.
Okay, I've got a picture that I'm going to show from NASA, and they talk about it as a false color image, but I'd be very interested in your comments because it's quite an interesting photo.
That's what false color means. They just assign.
But would you say that what you
There's
got?
definitely green there.
I don't think that's a NASA image.
Yeah, thank you.
It's a nice image.
I'll try it again and see if NASA can come through for me this time. Well, I seem to have more problem than most of you guys. So this is South America. Maybe I'll just open it and see here. Now, are you seeing that slide?
No,
Not yet.
we just seen you.
Shared the screen, Jeff.
Pardon me?
You haven't shared the screen. That's why we don't see it.
Okay. Perhaps. There we go. Do you have that?
Yeah.
Oh,
Yes.
good. Okay.
Working on it.
It's no longer the ocean?
No,
I don't see anything.
Oh, it's started, but it's not finishing.
We're moving forward. Great.
Yeah.
Your screen share is not working, Jeff.
Oh, so you're not seeing that yet?
No, it
It's-
says it's starting to share and it's just stopping there.
It's stuck.
I've got a lovely picture here. Too bad you guys aren't seeing it.
Well,
Have you
send-
pressed the second green button?
Yeah, the green button, ultraviolet. How's this? You getting that?
Yes.
Well,
Yeah.
that's the title page. Yeah.
Oh, good. Well, that's where we start. So when I'm going to be hosting, I often go with the iPod. NASA has an astronomy picture of the day, an APOD, and I do it for the date that I'm hosting. And this one really blew me away. They talk about it as a false color image of the Earth. Yeah, it's shot from the first lunar observatory that went up with Apollo 16.
Apollo 16, that's right.
So I'll give you a quick, it was developed by this guy, George Carruthers. This is him with the instrument here. It flew on Apollo 16 in April of 72. And they took up something like 172, 173 pictures with it. This one was just released in 2018, and it's quite interesting in that it so the details 10-minute exposure in the far ultraviolet, filtering atomic hydrogen, but picturing or transmitting atomic oxygen and molecular nitrogen. And it's basically, I think it was a proof of concept, and you can probably talk more about that, Chris Gaynor. But it shows basically the ultraviolet light impacting on the Earth and being absorbed in the stratosphere, not penetrating to the Earth. I'm assuming, and David, Dave Payne, this is where I'd be very interested in your comments. I'm assuming the red is the atomic oxygen, because it would be the ozone, and it would be the oxygen ion. And then I'm assuming also the green is the nitrogen, because that would be, it's much richer in the atmosphere. The atmosphere being, almost 80% nitrogen. Does that make sense, or is that an interesting interpretation of this picture?
Well, that's a good guess. I can't say either way. It
Okay.
sounds like a good guess.
Okay.
Yeah, that photo actually was released shortly after they came back, and I think it was 2018 was maybe when it was the APOD of that week. And so there is, literature out there about the pictures. The way that camera was set up was that the astronauts just set the thing up, and it had an automatic program that it did. And they set it up right in front of the lens, so it was in the shadow. And I actually happen to know, you saw the picture of with Dr. Carruthers, who was like one of the first black scientists to be hired by NASA, and I happen to know a friend of mine in the historical community has written a book about Dr. Carruthers, and the reason I know about it is because he's hired my wife to edit it. So it will be out. I'm not sure, probably next year sometime. So yeah, so that's the first telescope that was used on the moon, and so far the only one that I'm aware of.
Okay, well, thank you for adding that, Chris. It gives a little bit of depth. I couldn't find much interpreting this picture beyond several people saying, "Geez, we'd sure like some more detail about this picture." So I appreciate,
Yeah, I might be able to in my library find a write-up about it. So I'll see if I can find it and ship it over to you.
Oh, that would be very interesting. Thank you. I thought it was a very interesting picture.
There's lots of spectral lines that go all the way from UV down into IR, given off, but and they're used. Those spectral lines are used by different cameras to figure out what the spectrometry is. So it depends on what you're looking for, whether you want to shoot in the IR or shoot in UV or shoot in visible light. So, I mean, it's consistent that hydrogen and oxygen, hydrogen is the hydrogen bond between a molecule is broken easily by a UV light, but nitrogen is just tough as nails, and it's really hard to break a nitrogen bond. It's almost an inert gas because of that. So it's just knocking the electrons up some energy levels, and when they fall back, they give off UV light.
Interesting. So is your sense that they were, I think, trying to demonstrate with the photo the UV light impinging on Earth from the sun. So UVA, B, and C being the far ultraviolet spectrum, which would be completely absorbed in the ozone layer.
Yeah, that's where you'd have the molecular the atomic oxygen, right?
Yeah, yeah, exactly, exactly. So I think. So it would be, so you're saying it's absorbed and that's how the light is emitted then? Is that, do I
Yeah,
understand?
it's absorbed into the atoms by changing and then re-emitted.
Right, okay. Okay, super, thank you.
I had a
yeah.
question, David, if on your picture, if Jeff's done, I wonder in reading not the color and the element, but in the form, and Natasha mentioned it looked like something there, a squid, but is it reasonable to infer that the star in the center of that formation is exerting that influence, maybe through gravity or something? Like, are you interpreting the form itself of that gas?
Absolutely. The difficulty in interpreting the form is partly because we only see this in 2 dimensions. So we don't really know if that squid is actually engulfed. We actually know how far away the red stuff is, but we don't know how far away the blue-green stuff was. I don't know if I need to show it again.
So does that mean it's difficult to identify the source, like if it's gravitational from some
Well,
body?
certainly gravity doesn't really do much to gases. So it's really in the shape of the stars. There's other forces that are at play in the gases. But you're right, we talked a little bit about a sail being blown by the light. Well, that happens readily with hydrogen. So hydrogen gets blown by UV light into various shapes that we like, and generally cloud-like things that we like to photograph because they're pretty, but they're like clouds in the sky. When it comes to oxygen, which was the blue-green stuff, now that's quite a bit bigger molecule. So it generally creates fuzzy things. Like its shape is usually fuzzy because it's not blown around by light very much, or even solar winds, because it's just got so much momentum. And you get into things, there's supersonic flow sometimes, subsonic flow, and that all goes into the form. You've got a competition of, some of these gases have a viscosity, so they yield, they resist being deformed, and all sorts of things like that.
But the source of it must be important, right? To an astronomer, that where is this being emitted from and why? I'm just curious about reading the form.
Yeah. Now, some people say this is this. I don't know if I need to show the picture again. I can do that quickly.
Go ahead if you can pull it up, dude.
Okay, is that up?
Yep.
Yes.
So some people say this is deformed planetary nebula. So those happen when a star dies and it expels all its gases, and generally makes a spheroid type shape. And it comes in different patterns, whether it's getting blown around, but this one is like a squid. Like there are not many other pictures like it. So and this one was only discovered in 2011.
Oh,
We didn't even know that this was there until 2011 when someone imaged it. We said, well, this could be a central star, but what's making it push out? And yeah, it's kind of ethereal, if you will, that a lot of oxygen pictures, a lot of the blue in our pictures they don't give sharp shapes like the hydrogen does. But over here at this tip, you can see that it is making a hard frontal edge. So is something blowing supersonically, like faster than the speed of sound at that edge? Is there a wind in this outer stuff that you don't see in the interstellar medium? Is there a wind that's coming across that? There seems to be some circular orb. Are these stars that are engulfed that are creating that? It doesn't really fall into easily a category of known things.
Really interesting. Thanks.
Someone will figure it out. Smarter than me, but
What's it called?
it's called the Squid Nebula.
Oh.
David Lee, did you have an announcement that you wanted to make about the
Yeah, I just want to thank everybody that's sort of responded to confirming that they want to continue with the beginner's SIG. It was actually kind of overwhelming. I didn't, well, I knew there were a lot of people that actually come and go, but thank you for doing that. And the reason why I mentioned that is if you haven't done so, you will probably not receive a message from me. I'm starting to use, or I will start to use, the centrally administered distribution, which thank you, Chris Burse, for producing for me. And it's based on the list of people that said that they wanted to continue. So next week, November 5th, is when we're meeting. And I don't think we've really decided on what the topic will be, but we have a long list of topics that have been suggested. If anybody wants something in particular for November 5th, just let me know. Thanks.
Thank you. And Lori, did you have something you wanted to talk to?
No, it's okay. It wasn't, it was just, it was minor. So we're already like well into the time here. So I can wait till next week. I'm going to be the tech person, or not the tech person, but the host. So I can bring it up next week.
Thank you, Dory.
Absolutely. It's 9 o'clock. Is there anybody else that has anything that they want to bring up or just raise for the group here? Well, that being the case, thank you everybody for participating. It's been a very interesting session. And I guess we'll see you in a week's time.
Thank you, Jeff.
Thanks, Jeff.
Thank you.